In the vast, silent theatre of the cosmos, we often fear the grand and the loud, supernovae that outshine galaxies, black holes that swallow light itself. But what if the most dangerous thing in the universe is not a monstrous giant, but something microscopic, a particle so stable, so perfect, that its very touch could erase our world, converting it atom by atom into a new, bizarre form of matter? Tonight we journey into a chilling hypothesis at the edge of physics. We explore the story of the Strangelet, the universe's silent killer. To understand this cosmic predator, we must first look at ourselves. Everything you see, the chair you're sitting on, the air you breathe, the stars in the sky, is made of atoms, and at the heart of these atoms are particles called protons and neutrons. For decades we thought these were fundamental, but we were wrong. They are each made of even smaller particles, a trio of quarks. This is the bedrock of our reality, a simple, stable arrangement. But the universe, it seems, has other, stranger ideas. Our entire world is built on just two types of quarks, the up quark and the down quark. A proton, for example, is two ups and a down. A neutron is one up and two downs. It's an elegant, predictable cosmic recipe that forms the basis for every element in the periodic table, from hydrogen to uranium. It's the foundation of all we know. But the standard model of particle physics reveals this is not the whole story. The up and down quarks have heavier, more exotic cousins. There are 6 quarks in total, arranged in 3 generations: up and down, charm and strange, and top and bottom. Our stable universe, it seems, only uses the simplest, lightest ingredients available. Let's focus on one of these exotic cousins, the strange quark. It's much heavier than the up and down quarks, and crucially, it's highly unstable. When created in particle accelerators, it decays in a fraction of a second. This is a good thing. A universe full of stable, strange quarks would be a very different and perhaps impossible place for life. So what if we wanted to create matter containing these strange quarks? We would need to overcome the universe's preference for simplicity. Nature always seeks the lowest possible energy state, which is why normal matter is so stable. To force matter into a stranger configuration, you would need an environment of unimaginable pressure and energy. And such places exist. They are called neutron stars. These are the collapsed cores of massive stars, born from the fury of a supernova. A neutron star packs more mass than our Sun into a sphere just a few miles across. It is an object so dense, a single teaspoon of its material would weigh billions of tons. Here, gravity crushes matter with an unforgiving force. Inside this cosmic pressure cooker, the rules of normal matter begin to break down. Gravity is so intense that it overcomes the forces that keep atoms apart. Electrons are forced into protons, creating a sea of pure neutrons packed together as tightly as physically possible. It becomes, in essence, a single, planet-sized atomic nucleus. But what if the pressure increases even more in the deepest core of the neutron star? Physicists theorize that even the neutrons themselves might be crushed. If this happens, their constituent up and down quarks would be squeezed out, forming a new, exotic state of matter, a frictionless quark-gluon plasma, a soup of fundamental particles. This is where our story takes a truly bizarre turn. In 1984, physicist Edward Witten proposed a startling idea. He suggested that under these extreme pressures, this soup of up and down quarks could transform. It could become energetically favorable for some quarks to change into strange quarks, creating a stable mixture of up, down, and strange quarks. This concept is known as the strange matter hypothesis. It makes a terrifying prediction that this 3-quark mixture isn't just stable inside a neutron star, but is in fact the most stable form of matter in the entire universe, more stable even than the protons and neutrons that make up our bodies and our world. If this hypothesis is true, then the matter we consider normal is only a metastable. It's like a ball resting in a small dip at the top of a hill, stable for now, but not in the lowest possible energy state. Strange matter represents the valley floor, the ultimate ground state of reality. All it needs is a nudge to start rolling downhill. Now imagine a tiny fragment of this strange matter, a microscopic nugget containing thousands or millions of quarks. This tiny piece of the universe's most stable substance is what we call a strangelet. It would be incredibly dense, electrically neutral, and utterly stable, able to travel through the vacuum of space for eons. But a strangelet isn't just a passive piece of cosmic debris. It is an active catalyst, a seed of conversion. Because it represents a lower energy state, any normal matter it comes into contact with would face a fundamental choice: remain as it is, or convert to the more stable, strange matter configuration. Physics suggests the choice would be instantaneous. The mechanism is like a cosmic contagion. When a strangelet touches the nucleus of an atom, it doesn't annihilate it. Instead, it absorbs the nucleus's quarks, converting them and adding them to its own mass. The strangelet grows larger, and the process repeats with the next atom it touches, triggering a catastrophic chain reaction. This is often compared to the fictional Ice-9 from Kurt Vonnegut's novel, a form of water that is solid at room temperature. A single seed crystal of Ice-9 dropped into a river could freeze the entire planet. A strangelet operates on the same terrifying principle, but on a quantum level, rewriting the very nature of matter itself. So what would happen if a strangelet struck the Earth? Let's visualize this silent apocalypse. The strangelet, perhaps no larger than a virus, would pass through the atmosphere and the crust undetected. To it, our planet would be mostly empty space, but it would inevitably strike an atomic nucleus. The first contact initiates the conversion. That first nucleus becomes strange matter, releasing a burst of energy and joining the strangelet. The now slightly larger strangelet continues its journey, touching another nucleus and another. The conversion front begins to spread, moving outward from the particle's path. The process would be exponential. 2 nuclei become 4, 4 become 8, and so on. A wave of conversion would sweep through the planet at near the speed of light. The Earth's core, its mantle, its crust, all would be systematically and unstoppably transformed into a single, massive sphere of strange matter. It's important to understand this would not be a Hollywood explosion. There would be no bang, no mushroom cloud. It would be a silent, horrifyingly efficient conversion. The planet would shrink and collapse into a hyperdense, superhot quark star about the size of a city, a dead monument where Earth once orbited. This raises a crucial question: where could these cosmic assassins come from? The most likely theoretical source is the collision of 2 neutron stars. The forces unleashed in such a merger are among the most violent in the universe, creating a kilonova that could potentially forge strange matter and fling strangelets across the galaxy. Imagine 2 city-sized objects, each more massive than the Sun, smashing into each other at a significant fraction of the speed of light. The resulting cataclysm warps space-time itself, sending out gravitational waves. It is within this chaotic, high-pressure forge that strangelets could be born and ejected into the cosmic void. A second, more controversial source was once proposed: our own high-energy particle accelerators like the relativistic heavy ion collider, RHIC, or the Large Hadron Collider, LHC. These machines smash heavy ions together to recreate the conditions of the early universe? Could they accidentally create a stable strangelet right here on Earth? This possibility created genuine public concern and even lawsuits in the late 1990s and early 2000s. The fear was that scientists, in their quest for knowledge, might create a doomsday particle that could consume the planet. It was a terrifying thought that humanity could accidentally trigger its own extinction. However, the scientific community has a very strong and reassuring counter-argument to this scenario. It is based on a simple observation of the cosmos. For billions of years, nature has been running its own, far more powerful particle physics experiments in the form of high-energy cosmic rays. These cosmic rays, protons and atomic nuclei, accelerated to near the speed of light by supernovae and black holes, are constantly bombarding every object in the solar system. The energy of these collisions often vastly exceeds anything we can produce in our labs on Earth. If strangelets were easy to create, nature would have already done so many times over. Our greatest proof of safety is right next door, the Moon. It has no atmosphere to protect it. For over 4.5 billion years, it has been subjected to an unrelenting cosmic ray bombardment. If this process could create a planet-destroying strangelet, the Moon would have been converted into a quark star long ago. Its silent, cratered face is a testament to our safety. Furthermore, there are other theoretical reasons to be calm. More recent models suggest that small strangelets would likely have a positive electric charge. This means they would be repelled by the positively charged nuclei of atoms, making it extremely difficult for them to get close enough to initiate a conversion in the first place. There's also the question of the stability window. The entire doomsday scenario hinges on the idea that strange matter is stable at low pressure, outside of a neutron star. Many physicists now believe this might not be true. Strange matter may only be stable under the immense pressures where it is formed, and would simply decay if it ever escaped. Despite their theoretical nature, scientists are actively searching for strangelets. Experiments like the Alpha Magnetic Spectrometer, AMS, on the International Space Station are designed to analyze cosmic rays. Finding a particle with an unusual mass-to-charge ratio could be the first tantalizing clue that strangelets are real. Yet, after decades of searching, we have found nothing, not a single candidate. The strangelet remains a cosmic ghost, a perfect predator in theory, but completely absent in practice. Its non-discovery is, in many ways, the most comforting result in all of modern physics. So, we are left with a fascinating paradox. Strangelets represent one of the most terrifying ideas ever conceived by the human mind, a true doomsday weapon forged by the laws of nature. And yet all available evidence and observation tell us that we are safe, that our familiar metastable universe is, for all intents and purposes, here to stay. So we return from the brink. The strangelet remains a ghost in the machine of physics, a terrifyingly elegant concept, yet one that has never been seen. It teaches us that the universe is governed by laws we are only beginning to understand. Its stability is a delicate balance, and a single hypothetical particle could, in theory, unravel it all. While the threat seems vanishingly small, the idea alone forces us to look at the stars with a new sense of awe and fragility. Thank you for joining us on this journey to the edge of existence. What cosmic theory do you find most unsettling? Let us know in the comments below.